This is part 13 of the series Calculus Prerequisites, and we're going to start this part with a review of some parent functions. Now, what a parent function is the simplest function of a particular family of functions. The object here is that you should be able to recognize the parent function of any other given function on inspection just by looking at it and saying that looks like a so-and-so. And this is what we're really trying to go for. And even if you can't tell that right off the bat, you should know what the parent functions are and what they look like so that you can manipulate other functions into them. So let's take a look at the upper left one. This is a constant function. It's a straight horizontal line, and the form is y equals some constant. Then we have linear functions, and the form is y equals x. So you can shift these up, down, left, right. We're going to talk about transformations next. Then we have absolute value. They look like V's, either upside down or right side up. And a strange looking function is the greatest integer function. You may have seen these, hopefully you've seen these in the past in pre-cal. And they're discontinuous stepwise functions that the value of the dependent variable moves in jumps. So no matter what your x value is, from 0 all the way up to but not including 1, the y value is always 0 here. And then as soon as you get to 1, the y value jumps to a 1. And then the y value is always 1 no matter what the x is between x is 1 and x is 2. As soon as you get to x is 2, it jumps up to the next, and so on and so forth. Think of this as kind of a quantum type function where it only exists in jumps, not in between these values. So that's greatest integer. Quadratic, you should know that from the U shape, either right side up or upside down. Cubic, it's this little double U where you have the U here and then the same copy of it down below. That's a characteristic shape of a cubic. Then we have square root or radical function. Cube root. Now, a lot of people get cube root confused with the cubic. Notice the difference that this cube root is going straight and then going vertical at 0, 0, whereas this goes up and straight horizontal at 0, 0. So these are different, but they look kind of similar. Then exponential, logarithmic. We learned that this and this are inverses of each other. That is, the reflections across the line y equals x across this line. Then we have reciprocal or rational functions, and they have this characteristic double asymptotic behavior here. And then we have all the trig functions. You have sine, cosine, tangent, which are the yellow functions, and then cosecant, secant, and cotangent, and those functions we're going to be looking at in great detail when we get into calculus, but you need to be fully comfortable with trig manipulations. We're going to do that next in the next part probably. So those are just a general review of the parent functions. What we're going to look at now is transformation of these parent functions. What happens to functions when we modify certain parameters, and take a look at the effect on the function itself so that we can manipulate one function into its parent or determine what's happened from the parent to get to that particular function. And this is going to be important to us because we're going to have to evaluate the behavior of a particular function based on the characteristics of its graph. So let's take a look at some transformations. So remember, a transformation is simply a changing of a function's position, orientation, shape, or size. And the transformation function, or the function being transformed, we're going to call f of x. And the image, or the transformed function, we're going to call g of x. We can do all these different manipulations. We can take and multiply by some constant out here. we can multiply the x value by some value, we can add or subtract a certain value to the x quantity, and we can add or subtract some value to the y quantity. So we're going to look at what happens when we manipulate each one of either A, B, C, or D, or some combination of those. The first thing we're going to look at is translations. So translation means moving up, down, left, or right. Now the key to remember is that whenever you alter the x value, a value with the x, you're altering something with respect to the x-axis. So when we change our c value, we're going to shift the function either left or right depending on which direction we shift, what's the sign of this value. Likewise, when it's outside, when it's not with the x, this is with, inside these parentheses is with the x, this is not with the x, therefore this is going to affect the y-axis. So this is going to be a shift up or down. And we're going to take a look specifically at how altering this c and d values affects the functions. So let's take a look at that now. So we're going to take a look at the parent function quadratic, and the yellow is the image function after the transformation, and we're going to alter the c value here. We're going to change the c value. Now, as we said, this affects the left and right shift. Now, it's kind of counterintuitive, but if you think about it, it really isn't. What's happening here, when let's say we add 1 to this value, so we say c is 1. If c is 1, in effect what we're doing is adding 1 to our x value. So here when x is 0, x is actually going to be 1. So we're putting a 1 in for the function, and when we square 1, we get a 1. So when x is 0, y is actually going to be 1. The effect that this has is to shift the graph in the opposite direction of the sign here. So as you can see, as I move the c value to the right, increasing its value, the graph of the function is shifting to the left. And you notice when c is 1 here, we have shifted the vertex of this quadratic to the left 1 unit. Likewise, if we shift in the other direction, if we decrease the value to -1, we shift the graph to the right. So changing this c is always opposite its sign. So if you add a positive value here, you're going to the left, and if you add a negative value, you're going to the right. Now let's take a look at what happens with d. Let's bring this back to 0. Now d shifts up and down. What's going to shift is this vertex. And this is the exact right sense, because since this is outside of the x, when we add, we're adding to the y, so we're actually changing the resultant y value. So it changes exactly as you'd expect it. If we increase this d to a 1, you can see it shifts the graph up 1 unit, goes up 2 units, and so on and so forth. If we go to the left, decreasing, we go down 1 unit, down 2 units, down 3 units, and so forth. So shifting this with a positive number shifts the graph up, and a negative d shifts the graph down. Now let's take a look at what happens with some of the other values. Now we're going to look at reflections. A reflection is accomplished by changing the sign of either the a or b values. Now when we change the sign of the a value, we're reflecting in the x-axis. And when we change the sign of the b value, we're reflecting in the y-axis. So let's take a look at some of those reflections. Now for a reflection, I'm going to look at the square root function here. Now we said that changing the a value reflects in the x-axis. Let's think about how that makes sense. Since changing the a is affecting the y value, and we make the y value negative, when we have a positive y value here, it's going to go negative down here. So it's going to flip across the x-axis. The same thing with changing this. If we change the x value from positive to negative, it's going to flip across the y-axis. So that's what's happening. So to change the sign, we take the a and go from 1 to -1, and we can see that it's flipped across the x-axis. Likewise, if we do the same thing with the b value, let's bring this back to 1, and we change that to -1, and you can see it's flipped across the y-axis. So reflection is by changing the sign of either a or b, and just think about it logically as to what's happening here. When you change the y value to negative, it's going to flip across the x. Change the x value to negative, it flips across the y. All right, let's look at the next set of transformations. Now we're looking at vertical stretch and shrink, and when we change the a value here, we're actually multiplying the y value by a specific factor. And so when we change that y value, clearly that's going to cause a vertical stretch or shrink. And when we make this a larger number, a number greater than 1, it's a vertical stretch. And when you make it between 0 and 1, it's a vertical shrink. So let's take a look at that. So think of a vertical stretch as grabbing these two lobes and pulling up. It stretches it and moves them both inward. So when I increase this a value greater than 1, you see how the graph gets narrower. It's like stretching it out. And when I decrease it, when I go from between 0 and 1, you can see how it gets scrunched down. It's like us pushing down. So it's a vertical shrink. So this thing is pushing down this way. So that's vertical shrink, vertical stretch. Now let's look at horizontal stretch and shrink. With a horizontal stretch and shrink, we're manipulating this b value. And again, since we're dealing with the x, we're multiplying by the x value, so the effect is going to be just the opposite of what you think. If you multiply this, if the b value is greater than 1, then it's going to have the effect of actually doing a shrink. It's going to make the x value larger, which is going to push these things in from the sides. And by going between 0 and 1 with this b, it's going to have the opposite effect, and it's going to be a horizontal stretch. So let's take a look at that. So I'm going to modify my b value here. I'm changing my b value, multiplying my x by some constant over here, and that's giving us a bigger x value, which makes this graph go vertical faster than it normally would. So when I increase this number, it has the effect of drawing this thing in because it's going vertical faster than it normally would. So increasing the b value is a horizontal shrink. It's the same as pushing in from this side. And likewise, going the opposite direction, when I go from 0 to 1, you can see how it's a horizontal stretch. That is, I'm pulling these things apart because I'm multiplying this number by a value less than 1, which makes this y value increase slower. So it's going to get wider on both sides. So that's a really quick overview of transformations of functions. Let's take a look at some examples. In our first example, it's absolute value, and we're multiplying on the outside, so this is a vertical stretch. This is clearly the sine function. We have a vertical stretch, a horizontal shrink, and we're shifting to the left 3 units. So vertical stretch, horizontal shrink, shift to the left. Here is a linear function. We have a vertical stretch and a shift down 3 units. Here we have another absolute value, vertical stretch, a horizontal shift to the left 5 units, and a vertical shift down 1 unit. And last, we have a quadratic. We're going reflecting across the x-axis. It is a vertical stretch. We're shifting to the right 4 units and up 2 units. So you should be able to do all those. In the next part, we're going to look at composite functions. So I will talk to you in the next video.